Hello and welcome. I'm Shravan Nadkarni, team lead for TerraMind, and on behalf of my incredible team, we are excited to present our solution for this challenge: an integrated weather and climate risk forecasting system. Starting with a professional introduction, the core problem is the increasing volatility of climatic events. Current forecasting system often rely on siloed data, leading to delayed or inaccurate risk assessment. Our solution TerraMind integrates real-time weather data, advanced geospatial algorithm predictions, and API managed climate intelligence into one cohesive interactive platform. Let's dive right into the demonstration. As a front-end developer, I leveraged React.js for the UI and Leaflet.js to render a high-performance interactive geospatial map. A watch as I enter a location into the system immediately fetches and displays both real-time meteorological data and crucial risk forecast for that area directly driven by our Python backend.
I'm Shravan, the API manager. Our system's reliability hinges on a robust and continuous data feed. My role was to establish and manage the integration layer, ensuring reliable, synchronized communication all across components like front-end, backend, and ML services. We coordinate multiple external and internal APIs. Externally, we rely on Open Weather API for meteorological data and NOAA API for climate history records. As you can see in the API app.py service definitions, each API is compartmentalized to guarantee data integrity and is managed with robust error handling. This API management process is vital. It allows us to retrieve and process high volume data sets efficiently, delivering the raw validated input needed for the backend aggregation and crucially for our sophisticated ML risk assigned assessment models. This guarantees a consistent, uninterrupted flow of critical climate intelligence.
Hello, I am Gokukrishnan EB, responsible for backend services and API integration. Our foundation is high-performance Python Flask server designed for rapid data orchestration and future engineering. I developed the core logic starting with weather services, which handles the geographic lookup, converting the user's location string into necessary latitude and longitude via the API coordinates route. This geometric data is then reused across subsequent endpoints to fetch general data from our integrated resources. The key is efficient integration. The backend acts as a data hub, retrieving the raw data, performing server-side data cleaning and and aggregation, and presenting it through tailored RESTful endpoints such as API climate impacts and API alerts, ensuring the front end only consumes the necessary optimized data payload.
Hello, I'm Parth Ghurke, and my focus was on two crucial phases: ensuring that the EnviroVision model is integrated efficiently and that the entire project is simulated deployed.
Array.
The trained EnviroVision model, as Ritesh mentioned, it works perfectly at real-time detection. We use it to process our new satellite images and generate a predictively layer for example, accurately detection the likely progressive of a tropical storm or the parameter of a wildfire. This output is made available by the backends of our folder, which is API slash ML forecast endpoint, which also integrates our supplementary ML time series and a regression model. And also we have implemented Windy API for real-time weather forecasting, which helps us to pure prediction metric. I manage the deployment of a full application stack. The entire system, front end, back end, and the dedicated ML services is containerized, which is containerized. This robust deployment architecture allows us for horizontally scaling and ensuring a high availability integrated climate forecasting system accessible to the end users globally. Thank you.
Hello, as a team leader of TerraMind, I am here to walk you through the technical architecture of our three core intelligence modules: YOLOVA detection, regression forecasting, and our Windy.com integration. First, for object detection, we implemented a detection pipeline distributed across the stack. In the backend file app.py, we have the satellite service class. This service stimulates the YOLOV8 output by generating specific detection objects for flood, wildfire, and deforestation based on our coordinate geometry. This data is consumed in the frontend app.js by the fetch satellite map function. Instead of a static overlay, we pass these detections and dynamically render them as a L.circle marker layers on the leaflet map, which is a library of JavaScript for implementation of maps. So we apply specific logics such as checking is near water source to validate flood detections before rendering, so that it will ensure high precision visual feedback. Second, we extend our forecasting capabilities beyond the standard 7-day API limit. We built a custom regression engine directly in app.js. We implemented the train TS, that is time series function, which mathematically calculates the mean, slope, and volatility of our historical weather data. These metrics are passed to the forecast TS function, which projects these trends towards to generate the data for our 30-day risk forecast. We also included a train regression function that calculates an R-square value, giving users a statistical confidence metric for our long-term flood and heatwave predictions. Finally, for real-time atmospheric visualization, we integrated the Windy.com API directly into React state. In app.js, we defined the getWindy embed src function. This function dynamically builds the iframe URL by injecting the active coordinate state. It is linked to a tracking overlay state variable, allowing the iframe to instantly switch between wind, rain, and pressure modes without reloading the component, providing seamless real-time context. By tightly coupling backend logic with frontend, the TerraMind and its statistical modeling and dynamically third-party visualization, TerraMind delivers a complete full-stack